So, in lecture 9 part 1, we discussed about the applications of equilibrium thermodynamics in electrochemistry, where we discussed about the electromotive force and how it is connected to the changes in Gibbs free energy. And then we also talked about the Nernst equation, and we talked about the cell potential in that lecture. So, in today's lecture, we will be discussing about the another application of thermodynamics or equilibrium thermodynamics, which is applications to of surfaces and interfaces. Now, surfaces and interfaces are extremely important, and particularly in terms of say catalysis, which we will be discussing in under chemical kinetics portion. And there we will see how basically the presence of a surface can lead to the adsorption of one particular reactant or many reactants together, and then how they help in breaking or the particular bonds in the molecule, and thereby providing the necessary energy of activation and or lowering the energy of activation of the energy barrier that the reactants would have required if it was in a if that we perform the reaction in gas phase. So, the presence of surface dramatically modulates the rates of reaction, but in today's lecture we will be discussing only on the thermodynamic aspects or the equilibrium aspects, how the surface actually changes the thermodynamics, how it is different from the bulk phase, that we will discuss today. Now, to begin with, you can think of a system with an interface, and when we talk about interface, it must consist of two bulk phases. Suppose these bulk phases I am writing as alpha and beta, and then there is an interface. So, this is one bulk phase, say we call it as a bulk phase beta, and similarly this is a bulk phase alpha, and this one we call it as an interface. So, this interface is between alpha and beta. So, it is between two bulk phases, between two bulk phases. Now, the question is how will you model this interface? Now, to begin with, let us try to understand what is the thickness of this interface. Now, you can think that this interface is actually of very thin dimension. The way I have drawn it is actually to some extent, not to some extent, it is highly exaggerated, because if you think that this alpha and beta are non-electrolyte, then you will see that this interface will be a few molecular thick. So, you can actually, to a good approximation, think that this interface has 0 thickness. However, it will have an area, because if you remember that the way we are drawing it on the 2D surface, do not forget that it is something like a cylinder. It is a cylindrical system. So, it has an area, the interface has an area, and each, this is alpha phase, this is beta phase. But now we are talking about, okay fine, there is an area of the interface, but does it have any thickness? And this thickness you can ignore it, and that model was provided by Willard Gibbs, where he considered that, well, we will consider interface to have some area of course, but with 0 thickness, which means the volume of the interface will also be 0. Now, this will be very important. So, this volume of the alpha phase we call it as a V alpha, the volume of the beta phase we call it as V beta, but volume of the interface, which we denote as sigma, V sigma, is nothing but 0, because the thickness is 0. So, it is nothing but the area times the thickness, which is 0, and that is why it is 0. Now, we will be discussing the thermodynamic properties of this interface. Now, before going into detail, let us try to understand how the energetics of the interface should be compared to the bulk phase. Suppose there is a molecule in the alpha phase and when it is in the bulk or inside the alpha phase, it is being attracted, or there is some kind of interaction, and this interaction the molecule feels from all sides, and to a good approximation we can think that the isotropic nature of the medium. So, you can think all these interactions actually average out. So, the molecule actually experiences no net force on its motion. However, when we bring the molecule on a surface, so suppose this is just a liquid, suppose this is water, and we are bringing one water molecule, or one say some molecule is dissolved in water, and we are bringing that molecule to the surface, and then we will see that okay fine, this molecule is having interaction with water molecules in all side, but in the surface there are very less number of molecules in the beta phase, because there will be some water molecules, very less number in the vapor phase if we carry out this in a cell tube. So, it will have an unbalanced force, the molecule will experience an unbalanced force, which means in order to bring the molecule from the bulk to the surface, we have to do some work, and this work will be definitely proportional to the increase in the surface area which is associated. Why there will be an increase? Because if we bring one particular molecule from the bulk to the surface, what effectively we are doing is that we are increasing the surface area. So, that will involve some work, and this is positive work, because here actually we are doing the work, not the system. We are bringing increasing the surface area of the system, and that is why the surrounding is doing some work, and that proportionality constant we call it as gamma, where gamma is known as surface tension. So, the surface tension can be defined as the work done per unit change in area. So, that is the definition of surface tension. So, it will have dimensions of energy per square centimeter or square meter, something like that. Now, think about it, for this when we talk about the surfaces or interfaces, we have to choose a particular molecule or particular component and discuss about its thermodynamic properties in phases alpha or phase beta and at the interface, which we denoted as sigma. Now, what I mean by that, think about it like say for example, we add some salt in water. Now, the question we are asking whether this salt will preferentially stay in the alpha phase, which is the liquid water phase, or in the beta phase, which is actually the water vapor phase, or it will stay preferentially in between the sigma or the surface region. Now, for salt actually we will see that it will preferentially would like to go into the bulk phase, but there are many other molecules that will preferentially would like to stay in the surface. Now, how will you quantify it? That is the first question. Now, for that let us assume that we are plotting the concentration of a substance as we cross the alpha to the beta phase. Suppose this is alpha, this is beta, and of course, this is sigma, and suppose along this direction we are varying, we are basically watching how the concentration varies, and let us also say that at this point we call it as z equal to 0, and the dimension of the system or the length of the system in this z direction is say b, it is some parameter, and at or we can actually call it as say something in terms of z, say we call it as a z max, and then at the midpoint where the interface exists we call it as z 0. Now, I am plotting the concentration of some species, say I am calling this species as I. So, I am plotting C I and how it is varying if I vary the z from 0 to say z max. Now, since concentration is an intensive property, it should not change, I mean it should be a flat line if we go from go within a phase, and then we may see a very interesting phenomena. So, here the concentration corresponds to the alpha phase, I am writing it as C I alpha, and suppose the concentration drops in beta phase. So, I am calling it as C I beta, And then the question is, how does it drop? Does it drop abruptly the way I have drawn by the dotted line? If it does abruptly, then actually there is it is just the alpha phase and the beta phase, there is no interface in between. But in reality what happens, you will see the concentration will slowly change like this, it will drop slowly and it will go like this. So, what you discover here is that the concentration here in the alpha phase, where this distance is just the Z0 distance, actually start dropping much before the Z0 is attained. It is not actually much before, I mean we are again exaggerating the thickness of the interface here, but the point here is that it starts dropping before it has reached the length has reached Z0. So, it start dropping and then it also start it is little bit higher also before it even after it has crossed Z0. So, you see here that the concentration should have been like this for the alpha phase, but it has dropped. So, this area corresponds to a negative area, as if the concentration is has dropped from its bulk phase concentration. Similarly, here you can see the concentration has actually increased compared to its bulk area. So, what you can see here, if we multiply this drop and the increase and addition basically and subtraction of this concentration, and first you add these two values of how the concentrations are changing, and then if you can multiply it with the thickness of this interface and times the area, then you get the volume of that interface, and then you can ask this question whether these two area, the positive area and the negative area, do they perfectly cancel. If they perfectly cancel out, then it means that the interface does not have any excess number of molecules. However, you may get a situation that the positive area is more than the negative area, which means in the interface you will get a net excess of molecules compared to the alpha phase or the beta phase. The way you have drawn it, and on the other hand you may get overall negative area, which means actually the concentration of the molecules in the interfacial region are actually less. So, based on that we will see that we can divide the molecules into different types. Now, the question is how do you how do you formulate the thermodynamics of this problem. Now, to begin with, we will just do the mass balance, in the sense that we know that the total number of molecules in the interfacial region for the ith species, that will be nothing but the total number of molecules minus the number of molecules in the alpha phase plus the number of molecules in the beta phase. That would be always true. Now, next thing is that we will start from the first law of thermodynamics. And for a reversible process, we can write it as the d cross q term at TdS, and then we can write it there will be some pressure volume work, and plus there will be some work which is also associated due to the increase or decrease of the surface area that we wrote as gamma into dA. Now, this is for a reversible system, of course, or reversible process, and this is also for a closed system, the way you have drawn it or we have written it. However, if you think that this component I, this is actually freely transferring between the alpha and the beta phase. So, because there is a gradient in concentration from going from alpha to the beta through the interface. So, we have to add some additional term for the reason is this system is an actually open system, because we see exchange of mass across the interface. So, the first law, in the first law we have to consider, if you remember your our discussion on chemical potential, this P is actually capital P plus gamma dA plus the way we write it, all the additional term due to the change of number of moles from one phase to the other phase, that we can write it as sum over mu I dNi. So, that we already discussed when we discussed the Gibbs free energy per unit mole or the chemical potential. So, where mu I is the chemical potential of the ith spaces. Now, this is also for reversible process, but now we have made it more general. We are considering for an open system where we added this extra term. Now, the question is how will you write this extra term? Let us just try to have a look. So, we know that what is mu I dni. So, if you ask this question, what is mu I dni? So, mu I will be the chemical potential, but you know that this chemical potential of which phase we have to define that. Now, at equilibrium you can approximate that not approximate, when the equilibrium has attained, you can always say that the chemical potential of a particular constituent, which we are denoting as I here, will be same in all the phases. So, mu I of alpha will be equal to mu I of beta will be equal to mu I of sigma, which means now we can just write it as something like mu I. Now, this term, now we can expand it as if it is sum over I mu I. Now, d of ni, but we already know that ni is nothing but ni alpha plus ni beta plus ni sigma. So, you can just write it like this, ni alpha plus ni beta plus ni sigma, where alpha and beta are for the bulk phases and sigma is denotes for the interface. So, what we get is a very interesting situation. Now, what we are going to do is that we are going to write the different terms, different terms in the sense that this du is nothing but we know that we can write it as the total U or the internal energy also as the energy of the alpha phase plus beta phase plus gamma phase. Just the same way we have written the number of moles for the alpha phase, beta phase or gamma phase. So, in that way if you write it, so what I am saying here is that you could write it as U alpha plus U beta plus U sigma, and then you could write it as du is nothing but du alpha plus du beta plus du sigma. So, that way we can actually write all the terms, and then you can ask this question that how these individual terms, for example, this du or ds, they change. Now, let us rewrite it once again. So, we are writing it du, instead of du I am writing as du alpha plus du beta plus du sigma is equal to, then we have tds, we will have tds alpha plus tds beta plus tds sigma, plus there was a pdv term. So, I will have pdv alpha plus pdv beta, but there will be no pdv sigma because the dv of sigma or v of sigma is 0. So, there will be no pressure volume work associated for the interface because the interface has 0 thickness and hence 0 volume. And then we have one term which was a d gamma, and remember that is only associated with the interface. So, it is not associated with the bulk phases. So, that a d gamma term is very specific for the interface. And then we have all the mu terms where we can write it as mu I dni alpha plus mu I dni beta plus mu I dni sigma, and that is only for one particular component. For if we have many components, then we have to take a summation over all these components. So, now we can just equate term by term. So, we will get one equation for the alpha phase, one equation for the beta phase like this, and then we will also get one equation for the gamma phase, and we are only interested in the equation for the gamma phase because we are only considering the thermodynamics of interfaces. So, we can write that du sigma is nothing but TdS sigma plus A, remember that there is no PDV term for the surface, A sigma sigma d gamma, plus it will be sum over I mu I dni sigma, because mu i's are equal. So, I am not writing mu I sigma or mu I alpha or mu I beta. Now, the question is, so this is basically the first law for the surface or the interface in this case. Now, we can always integrate it. We can think that the system is going and undergoing a change from state 1 to state 2, and then if we integrate between these states, you will get nothing but something like u2 sigma minus u1 sigma is equal to T of S2 sigma minus S1 sigma plus some area times this d gamma, or it should be actually gamma dA. So, if we go back one slide, so we see that it will be gamma dA, it is not A d gamma. So, we can correct for that. So, it will be A gamma into dA, and that A is associated with some area. So, it will be gamma dA instead of A d gamma, and then we can write it as the surface tension times A2 of gamma minus A1 of gamma, not gamma, it is sigma, and then we have the sum over the terms, which are something like, we can write as if we integrate n I 2 minus n I 1, and this is for the interface. Now, what we can conclude from here, the internal energy for the interface can be written. You can see that this is basically difference between the state functions. So, u is a state function. So, we can also write it as internal energy is nothing but T s sigma plus gamma A sigma plus mu I n I sigma. And now, you can take again the total derivative, and you know how the total derivative is done. So, you have to write TdS sigma, plus there will be a second term which will be S dt sigma. So, the same approach we also used when we discussed the Gibbs-Duhem equation, when we took wrote the Gibbs free energy as mu I dni, mu I, and then integrated it to get mu I ni, and then again took the differential to get mu I dni plus ni d mu I, and we said that ni d mu I term has to be 0. The same approach we are going to do here. So, we have here gamma dA, and similarly we will have A d gamma, plus we will have sum over I mu I dni sigma, and here we will have sum over I dni, sorry, it will be ni sigma into d mu I. So, we can see by comparing this equation and this equation which we just got, that this part must be equal to 0. We can make a further approximation, and we are going to make another approximation where we will talk about only the isotherms. So, basically we are keeping the temperature constant, which means now the S dt will also be 0. So, what we get from here is that we have A d gamma plus sum over the constituent I, and written as n I sigma d mu I is 0. Now, we can rearrange it a little bit, and we can get the value of d sigma. This is remember, this is for a reversible process, and this is for an open system, because we have made it very general, and also this is for open system, and we also made it for constant temperature, because we have dropped the S dt term. So, d sigma is d omega is nothing but minus n I sigma divided by A into d mu I. Now, remember what was n I sigma? Ni sigma was the total number of moles minus the moles of the in the present in the bulk phases like the alpha or the beta. Now, if you remember this particular curve where we discussed about these positive and the negative areas or the regions of the concentration. So, this concentration multiplied by the small thickness and then multiplied by the area will give you the number of moles. So, those number of moles are actually will be excess if this positive area is more than the negative area. It will be the other way around if the negative area is more, and it might be 0 also if this area to area perfectly cancels. So, what we are asking right now is that we have got an expression for gamma, which is surface tension, connecting to the number of moles in the interface, which actually is corresponds to this excess number of moles in the interface divided by area. So, we see a very beautiful relation here, that this quantity, the number of moles or which is excess in the surface per unit area, that we term as surface excess, and we write it as gamma I. Sorry, it's gamma I, and we call it as a surface excess. So, it will be nothing but gamma I into d mu I, sum over I. So, we can now also say that this gamma I is nothing but a property of the interface. That is why I am keeping notation sigma there. So, now we can actually plot the sigma versus the concentration, but before that let us try to understand what is the sigma. So, we can for that we can actually expand it a little bit. So, suppose we have only one component. So, I am writing it as 1, it is a particular component, but we always write it as this, instead of writing it as gamma suffix 1, we always write it as a component with respect to the bulk phase. So, 2 here denotes that how many molecules are there in the interface compared to the bulk phase. So, for example, to give you a feeling that I have an alpha phase, say it is water, and then I have air here where you can have water vapor, and here I have liquid water, and then I am adding some salt, and then I am asking how much excess I have. So, it is basically gamma 2 with respect to the 1 phase that we are writing for a particular component, that one component. So, it will be minus d gamma mu to 1 and times mu d mu 2, because the 2 we are writing it for the component, because there are some component of the particular thing which are also in the liquid phase or in the bulk phase. So, so this 2 is for component in interface. So, that will tell us the surface excess. So, it is excess with respect to bulk, that is why you are writing 2, and in parenthesis we are writing as 1. So, it is with respect to the bulk, and it is component in bulk phase. So, if we write it the mu in terms of our if we expand it in terms of the standard chemical potential, we know that it will be nothing but mu is mu 0 plus RT ln activity of the species. For if it is species I, we will write it something like that. So, if I take the derivative, this term will be 0, because mu 0 is nothing but a standard state activity, standard state chemical potential, the derivative of which will be 0. So, we will be left with only RT ln activity of this particular component. So, we can write it as minus gamma 2 into RT ln, and instead of taking the derivative, we will just write it as d of RT ln AI. So, what we get right now is this quantity gamma to 1 will be nothing but minus 1 over RT into del gamma del ln A2. Instead of I, we can write it as A2 because we are considering the activity of that component at the interface, and that was taken at constant temperature. Now, for dilute solution, we can approximate the activity to be equal to the concentration. So, we can write it something like this: d sigma d, gamma and del gamma and del ln C2 at constant temperature. It will not be actually C2, it will be, to be very precise, it will be C2 by C0. It has to be always be divided by the standard state, which is 1 mole per liter. Now, you see that if we plot the gamma versus T plot for and look at different substances, you will see for few substance actually the slope will be positive. The positive slope means del gamma del ln slope is also positive. So, what you will get from here, it is not versus T, it is versus C2, the concentration of the molecule in say some phase, which is in say alpha phase. Now, what you see here is that we have an increase here, and this increase or the molecules which show this type of increase, we call it as a type 1 molecule. Now, type 1 molecules means actually there is a positive slope, which means actually the gamma, the surface excess, will be negative because there is a negative sign here. So, these molecules will preferentially would like to stay in the bulk. Examples are something like salt, or say organic compounds like sugar, say for example sucrose or glucose. They will preferentially would like to stay in water phase because they are highly water soluble. There are some compounds which actually show a slight negative trend, which we call as type 2. These are organic compounds with COOH or alcohols, which actually have some hydrophilic part and a hydrophobic part, and those hydrophobic part would actually would like to go into the air phase in the hydrophobic, in the sense they repel water. They actually do not repel water. So, water-water interaction is more than the water and alkyl chain interaction. That is why they prefer to stay away from water, but there the slope is not that much negative, in the sense that the gamma is not that much positive also. So, they preferentially accumulate in the interface, but not much. They actually stay both in the bulk phase as well as in the interface. And then you will also have a third type of molecule where you will see a large drop in that concentration, a large drop in that slope, which means actually this is very highly negative, this slope, which means gamma is highly positive, and these molecules, which we call as type 3 molecules, which will show preferential accumulation in the interface, and they are collectively called as surface active agents, because they are activating the surface as if they are increasing the surface area, because they are going into the surface more and more than in the bulk phase. Surface active agents, or in a short form they are known as surfactants. And the examples of surfactants are like soap molecules. So, these long chain fatty acid molecules which for example under salts like sodium stearate or sodium palmitate, they have a very long alkyl chain, and they also have a hydrophilic head group. So, what they do is that if this is the water air interface, so these molecules will actually interact with their hydrophilic head group through the water, and then their alkyl chain actually pops out from the water from the interface, and then they just arrange themselves nicely in a parallel fashion. So, you see there is a large drop, and then after some threshold concentration it is not changing much, because they have almost formed a kind of monolayer on the surface, in the sense that if you add more and more, so then there is not much space, that they are a highly crowded molecule. And then if you still keep on increasing, the surface excess won't change much, because now the molecules will go try to go inside more and more into the bulk phase, because there is no space available to go into the interface. So, in this chapter, what in this section what we just discussed is that first we started with the thermodynamics of interfaces, and we talked about a model which was developed by Willard Gibbs, and we said that we can actually ignore the surface area, or the not surface area, so the volume, by saying or by assuming that the thickness of the surface is vanishingly small, which we can take to be 0. And then we defined the surface tension, and then we just tried to write the first law for the bulk phases as well as the interfaces, and we gave a concept of what is meant by the surface excess, which we defined later mathematically. And then we saw that we can actually divide this segregate this first law into different pieces, one for alpha phase, one for beta phase, and one for the bulk phase. And then we got equation like this, and then we used some approach like the Gibbs-Duhem equation, the similar approach which we used to derive the Gibbs-Duhem equation, and we got this relationship. And we also made an additional constraint that we are considering the constant temperature to get an isotherm, and then we found that we got a relation where which is basically a relationship between gamma and which is basically the capital gamma, the surface excess, with small gamma, which is surface tension, and how it is varying with the activity or the concentration. And this is known as Gibbs adsorption isotherm, and we saw that based on the Gibbs adsorption isotherm, we can actually differentiate molecules into 3 different categories, like type 1, type 2, and type 3. And type 3 molecules are very interesting, which are known as surfactants, because they preferentially they have a very high tendency or propensity to go into the interface than being stayed at the bulk surface or at the bulk phase. So, here always remember that we are plotting it as C2 alpha, meaning we are actually increasing the concentration in the alpha phase, which means the concentration in the interface and the other phases will also increase. And we are writing it as 2 1 in the sense that it is basically chemical potential of the substance 2. It's not actually component in the interface, rather we could, instead of writing it as a component in the interface, we could write it it's a first component and the second component, in the sense the first component here is the, say, salt or the reverse Meissen, or the not reverse Meissen, sorry, the surfactant molecules, and the first component here is just water. So, it is how much excess you are having of component 2 in presence of component 1, which is water. Water is always present. So, 2 and 1 are here for the components, is not for the interface or the bulk. Interface and bulk, we are still preserving this alpha and beta notations. So, we will be just closing this discussion here, and in the next lecture we will be discussing about the kinetics of chemical reactions, where we will be discussing how fast or how slow chemical reactions proceed, and we will devise models to explain those things. Thank you.